네요.
네.
네.
그럼 1시에 딱 그 사인 주시면 시작하도록 하겠습니다.
예, 예. 그리고 제가 거기 교수님 잠깐 소개를 해드리고
네네네네.
하려고 그러는데 교수님 홈페이지에 아주 잘 나와 있더라고요. 그래서
아, 예.
읽어도 될까요? 그렇게?
네네,
예,
괜찮습니다.
그렇게 하겠습니다. 아, 교수님 뭐 연구 업적이 어마어마하십니다 보니까요.
하지 않습니다.
아유, 겸손의 말씀. 갑자기 오늘 날씨가 추워져가지고
예, 오늘 춥더라고요.
매일 추운 날이라고 올 들어서.
11월, 예, 맞습니다.
어디에서 진호 교수님 조남이 어떤 분이세요?
그 데이빗 제이 러브라고요. 데이빗
아,
러브라고.
러브
네.
유명하신 분이죠.
네, 잘 못 들었습니다.
유명하신 분이라고 유명하신.
예, 예, 그 당시에는 유명했는데 지금은 네.
뭐 연구하시
저랑
너무 고생하셨죠?
저랑 3살 차이입니다, 지도 교수가.
아, 그러시구나.
네. 제가 박사할 때는 되게 젊은 교수였는데 지금은 아닙니다.
그러니까 뭐 좀 빡세게 좀 하는 게 있었겠죠.
예, 저희 지도 교수가 좀 더 그 빡센 게 있어가지고요.
네.
제 지도 교수의 지도 교수가 그 로버트 히스인데,
그러니까
예,
다
예,
그물이잖아요. 네.
그렇죠. 이렇게
그러니까
지도 교수가 굉장히 예, 학생들 힘들게 하는 게 있어서.
아이고 고생하셨고 그래서 그런지 약간 큰 업적 많으신 것 같고요.
음.
교수님 딱 지금 정각이 됐어요. 그래서 교수님
네,
소개를 하겠습니다. Okay, hello everyone. We have another guest speaker named Professor Jiho Song. Professor Jiho Song received the bachelor and master's degrees in electrical engineering from Seoul National University in 2009 and 2011, respectively, and received a doctorate degree in electrical and computer engineering from Purdue University in 2017. He's currently with the Department of Electrical and Electronic Engineering, Hanyang University, as an associate professor. Before joining Hanyang University, he was a senior researcher with Motorola Mobility, Chicago, Illinois, United States from 2017 to 2018, and an assistant professor with the School of Electrical Engineering, University of Ulsan from 2018 to 2022. His research interests include the design and analysis of millimeter wave, sub-terahertz, and vehicular communication systems. He was awarded the Bronze Prize in Samsung Electronics 23rd Human to Paper Contest in 2017. Please welcome Professor Song.
thank you for your introduction, Professor Joe. So, good afternoon, everyone. Thank you for coming to my presentation. So, my name is Jio Song. First, I want to thank you for giving me this great opportunity. So, this is my brief introduction, and I'm going to skip this slide. And I'm going to show you a big picture of today's presentation. So today's presentation focuses on transmission and reception techniques for multi-antenna system in sub-terahertz and vehicular communication networks. Since I'm not fully familiar with everyone's background in MIMO beamforming topics, I'm going to begin with a brief refresher on the fundamentals and then transition to the related research topics. So today's presentation is going to be broken down into the following sections. First, I will briefly introduce the fundamental physical layer beamforming techniques for MIMO systems, and then I will briefly present my previous beamforming related research topics. So if you have any kinds of questions, please feel free to ask any kind of question if you do not understand any contents. So from now on, I will show you a big picture of today's presentation. So new mobile services in 6G networks are quite distinct from the traditional human-centric communication from the perspective of network throughput and latency and reliability. So we are now developing new transmission and reception techniques in order to meet this demand for the new network, which is 6G networks. So we will frame today's talks around these three themes, which is the massive communication, ubiquitous connectivity, and sensing as a services. So first, I'm going to introduce topic which is associated with the large-scale MIMO system. On antennas, effective aperture determines how much incoming energy it can capture. So in free space, as the carrier frequency goes up, the radio link is going to suffer more path loss for the same physical antenna size. So at millimeter wave frequencies or sub-terahertz frequencies, the wavelength is going to be very tiny. And so the same size antenna panel can hold hundreds or thousands of small elements. So on the slide, you can compare the single antenna element at 3 gigahertz and dense array at 150 gigahertz. As you can see, more than 2,500 antennas can be packed into the same array. So next thing you need to do is that you need to combine the receive signal which is at each antenna element. That's what we want to do here. So in order to exploit the full benefits of large-scale MIMO system, we need to know the channel state information. The channel state information between the transmitter and receiver must be estimated and quantized and fed back to the transmitter for the purpose of exploiting the beamforming techniques. However, if we consider the antenna array, which include a multitude of antenna elements, more than 1,000, more than 5,000, or something like that, it is not easy to estimate and quantize this kind of downlink channel due to the large dimensionality of the extremely large massive MIMO system. So in order to solve this kind of problem, we are now developing the channel estimation algorithm by exploiting a low channel training overhead, and we are also developing the low complexity channel quantizer which utilize a low feedback overhead. So in this section, I will introduce the fundamental physical layer beamforming techniques for MIMO systems. So let's compare MIMO channel under the spherical wave and planar wave assumptions. We can characterize the channel by utilizing the phase, pro phase progression across the antenna element at the both transmitter side and receiver side, since the progression defines the array response of vector. The radio signal from which is transmitted from the transmitter travel at the speed of light. However, because each element sees a different radio path length, the received phase are not identical. So when the transmitter and receiver are sufficiently far apart, the arriving wavefront, for example, you can see that this one is the wavefront, and as you can see, if the transmitter and receiver, the distance between the transmitter and receiver are far apart, the wavefront, arriving wavefront, is going to be effectively planar, and the inter-element phase difference is going to be approximately linear, and then this can be captured by using the far-field spatial frequency. So as you can see, by using only this parameter, we can characterize the array response vector of channel. However, when the distance between the transmitter and receiver are not large enough, for example, in this kind of near field regions, the wavefront is going to be spherical, and then the phase difference cannot be modeled by using this single parameter alone. I mean, we need to utilize the single linear parameter and additional non-linear, which is range-dependent component. And then we will call this parameter as near-field beam focusing parameter. So in order to characterize the channel vector in near-field region, we need to utilize two parameters, which is far-field spatial frequency and near-field beam focusing parameter. So in today's presentation, we are going to consider those two channel model, both channel model, which is near field channel model, which can be characterized by using those two parameter, and far field channel model, which can be characterized by using linear parameter, single parameter. So let's consider the far field channel for the uniform linear array first. In the far field, the incoming wavefront is effectively planar.